Okay, so let's look a little bit briefly at the 10 to 20 day mode. As we said before, the zonal scale of the 10 to 20 day mode is very local compared to the 30 to 60 day mode, which extends all the way to the Northwest Pacific, tropical Pacific, and is associated also with the East Asian monsoon. The time scale 10 to 20 days and the zonal scale etc. have to be explained, and unlike the 30 to 60 day mode, which has generally received attention for a long time, even though we don't have a fully accepted theory for it, the 10 to 20 day mode is received much less attention. But this paper by Chatterjee and Goswami from 2004 explains the mode basically by looking at the filtered structure and the phasing of the structure associated with the 10 to 20 day composites to fit a model to it. So here is the northern summer composites of filtered wind and outgoing long wave radiation. Then the dark shades here are the positive OLR anomalies, and the contours are negative OLR anomalies. And again, you remember negative anomalies in general are with respect to the seasonal mean, because you're bandpass filtering. That's below the seasonal mean, so you have a convective phase, and you have non-convective phase when you have OLR that's positive. But the main thing here is that you look, this filter time series has been split into phases, phase 1 to 15, using an EOF technique, which I'm not going to go into, but it is similar to the MJO kind of phase structuring using meridional and zonal winds and OLR, and using EOF on them to generate a phase of how the 10 to 20 day mode propagates within the domain. And the relative verticity of the composited winds averaged in the deep tropics between 5 south and 5 north is shown here to basically argue, and here are the phases shown again. You can see these are the phases derived from EOF technique. These are the longitudes. So you see the clearly westward propagating feature of the 10 to 20 day mode, which is known from observations. And we know that the amplitude of the 10 to 20 day mode is as strong as, or as large as, the 30 to 60 day mode, and the phasing of the 10 to 20 day mode and the 30 to 60 day mode together tend to determine the active and break phases of rainfall over the Indian subcontinent. So that's a critical contribution to the intraseasonal variability, which is what we are trying to understand here. The main story of the paper is this structure, which has got this cyclone-anticyclone pair with low OLR, convergence, rising motion, and the anticyclone, obviously you expect downwelling subsidence and high OLR or non-convective phase. That's in phase 8, and this is for phase 1, where you have now essentially switched the circulation. So you have the cyclonic phase over here and the anticyclonic phase over here. So you can see that if you don't know what a Rossby wave is, you can look up the other podcasts I have in my tropical dynamics course. But this is consistent with a equatorial mode number 1 Rossby wave, and the speeds, I think about 3.8 meter per second, is consistent with the Rossby wave as well. So then you have to explain, if it's a equatorial Rossby wave cyclone-anticyclone pair, why is it shifted to the north? So the Chatterjee and Goswami paper builds a model to try to explain it. This is just showing the latitude pressure section of the zonal wind composites in contours and colors, with the arrows showing the meridional and vertical velocities in pressure here. Pressure velocities are very small, vertical pressure velocities are very small. If you don't know what that means, basically the vertical coordinate in the atmosphere typically it tends to be pressure, because it's a nice way to project onto the naturally varying vertical structure of the atmosphere. And then the equations provide you vertical velocity in the pressure coordinate, which obviously tends to be much smaller than the meridional and zonal velocities, so you tend to scale it to put it on the same diagram. So you are looking at section here 85 east and 10 north and 7 south, just to understand the zonal wind. So here it's negative, so shaded numbers are negative. Zonal velocity means they are easterlies going from east to west, and the contours are positive, so they are westerlies. So you can see that along 85° east, along this longitude here, we are basically capturing this structure that we are looking at in this top view. So you have westerlies here with subsidence, and you have easterlies here with northward meridional winds with some vertical velocity here, ascent, that you can see, which is consistent with the cyclone anticyclone we saw before. And looking at longitudinal sections, this is at 10 north and this is at 7 south. These are just the zonal wind structures, again easterlies and westerlies, not so so you can see the limited zonal scale better here as well. So this is the 10 to 20 day mode, and here is the 7 south section, which is spread out a little bit more here. So you're capturing this zonal wind structure, at 7 south here. Okay, so the main question they answer is, why is there a Rossby mode structure to it, and why is it shifted northward? And they use a model, put in a boundary layer, and show that the entrainment term, the cyclone anticyclone terms, produce convergence and ascent or descent, divergence, convergence, ascent, descent, verticity, and that provides you the unstable excitation of the mode number 1 Rossby wave, that gives them the structure and the time scale in the right range of 10 to 20 days. And then they argue that this shifting is done by the background mean widths. Okay, so that's one of the good papers that's giving a consistent mechanism for where the quasi-bi-weekly mode and that time scale and spatial scales come from. This paper argues that the quasi-biweekly mode is quite common across the globe in the tropics, and it's not just restricted to the monsoon domain. And you can see these, there are mostly westward propagating ones, but there are also eastward propagating ones. This one is going from the equator, equatorial deep tropics westward, or going north and then turning eastward. There is eastward here, but the eastward going ones typically have this dashed arrow coming from the fronts from the extratropics. So there is the general argument that mid-latitude Rossby wave is involved in the eastward propagating quasi-biweekly modes, whereas the maybe tropically generated unstable Rossby wave is excited in the tropics are involved in the eastward, in the westward propagating quasi-biweekly modes. Okay, so you can read up the paper, but this is mostly, as I said before, these are basically taking observations, filtering them, finding the time scales, and then explaining consistently what is observed. They don't necessarily completely explain the mechanisms, fundamental processes by which the scale selection happens, but the explanation given in Chatterjee and Goswami in terms of the boundary layer frictional convergence entrainment generating unstable Rossby modes, Rossby wave, and then background winds shifting it northward is also a consistent but mechanistic explanation for the propagation of the quasi-biweekly mode. Okay, so that's a quick introduction, but if you want to read more, you can follow up with the paper. One thing to remember is that the 30 to 60 day mode and the 10 to 20 day mode have spectral peaks in the intraseasonal oscillation, and their phasing does determine the active break periods, so they are both very important. So to the extent that we follow the engineering approach of predicting those without necessarily understanding the processes, somewhat like cyclones, many processes are not understood, but the models are capturing the forecasts are doing pretty well, so that's what you focus on. And if the models are capturing the processes and accurately able to forecast, then you can maybe diagnose the models and advance process understanding. Typically you would want to use observations, find a hypothesis, take more observations to build a theory, and then test the theory, build models, etc. But sometimes the engineering approach is that the full GCM captures some processes that are not yet understood from observations, and then you can use the models to tease apart the details of how these processes work, because often they are very non-linear. So the boundary layer processes interacting with the free troposphere and so on are not easily built with simple models, so full DCMs may help in that sense.